Hey, I'll be going over question number 1 from the 2012 FRQ section of the exam. It's Calc BC. Um, so it's just basically a table problem, and to save time, you can pause the video and look at the problem. I've highlighted the important stuff that we need to solve A, B, C, and D. Alright, so starting with part A. In part A, we are asked to approximate W prime of 12. So using the difference quotient, it's W15 minus W of 9 and 15 minus 9. So I've basically, like it says, one from the left and one from the right, and that is from the table. So one from the left, one from the right, and then this is the formula for the difference quotient. You have 15 minus 9 at the bottom, and then W15 minus W of 9. So from the table, we can see W of 15 is 67.9, and W of 9 is 61.8. 0.8. And then that's over 6 because 15 minus 9. And then once you do that, you get 1.017 Fahrenheit per minute. It's about that number. So the second part of this problem, it tells us it's basically explaining what we found. So we found approximate instantaneous rate of change of W, which means that the temperature of water at T equals 12 minutes is 1.017 degrees Fahrenheit per minute. So at that time, the temperature is actually increasing. So that's what we have found. That's all it means. So moving on to part B. So in part B, we are given the integral 0 to 20 W prime of T dt, and because of the fundamental theorem, we can just go ahead and say that this is, rewrite it as W of 20 minus W of 0, and so from the table, W of 20 is 71, and W of 0 is 55. So you plug in 71 minus 55, you get 16 degrees Fahrenheit, and when we are integrating a rate, the net change in the temperature of the water in degrees Fahrenheit on the time interval 0 to 20 is 16 degrees Fahrenheit. So because when we are integrating a rate, therefore this statement is going to be true, and that's all that's asked from us in part B. Now going on to part C. In part C, we're supposed to find the approximate average value of the average water temperature. So since we are doing the average, it's going to be 1 over 20 integral bounds being 0 to 20 W of T, which is about, and this is, by the way, it also asks us to use the left Riemann sum. So this is, don't forget the 1 over 20, so put the 1 over 20 down, and then W of T using the table, so from 0 to 4, it's going to be 4, so you plug in the 4, and the left point, since the left Riemann sum is 55, and then 4 to 9 is 5, and then left point 57.1, and then 6, and then 61.8, and from 15 to 20 is 5, and the left point is 67.9. And once you go ahead and put all that in the calculator, you'll get 60.79. Why did we do that? So to make sense of it, actually in the problem we are given that we're told that W of T is increasing, and therefore just know that a left Riemann sum underestimates the integral, and if underestimates the integral, so our approximation of the average temperature is an underestimate as well. That's all for part C. So moving on to part D. Also another problem where we're going to be using the fundamental theorem, and just in case if you are a little rusty on that, it is if it states that if f is continuous on closed interval a to b, and f is the indefinite integral of f on the interval a to b, then the integral bounds being a and b, f of x dx equals the antiderivative of big F of b minus antiderivative or big F of a. so that's a quick recap. So we are given the integral bounds being 20 to 25, w prime of t dt, and if we integrate rate from, so because of the fundamental theorem, if we are integrating rate from 20 to 25, then we can go ahead and say w of 25 minus w of 20, similar, it looks like that. So we're just rearranging here, so w of 25 equals w of 20 plus our starting equation, so or expression. So integral of bounds being 20 to 25, w prime t dt. So we can just plug in numbers from the value from the table. So w of 25 is 71. Sorry, I mean w of 20 is 71, not of 25. Like you can see from the table, 20 is 71. So this whole, it's approximately 71 plus, I get this 2.043. Using the calculator, I just plug in this integral, and then this is the number you get out, 2.043. And that equals 73.043, and don't forget the units, degrees Fahrenheit. And that's all. That is your final answer for part D, and that's all for this problem.